All right. Hello everyone. This is going to be the post-contest discussion for the Starters 125 Division 2. All right, we'll be discussing 4 problems in this contest. Let us start. All right. We'll read the first problem. It's pretty simple. You were given a problem named fake certificate. It read that there was a binary string or S that was given of length N, and you were representing the attendance sheet of Alice by that string S. So if let's say SI was 1, that means Alice went to school. Otherwise, SI was 0. So now Alice wanted to increase her attendance and she could have performed the following operation at most once. What is that operation? You choose any substring of S where Alice was absent every day, and you can give a medical certificate for this period and you will be marked present for the whole period. All right. So a continuous string, a continuous segment of 0 where she was absent can be converted to a whole 1. This is the crux of this statement that is given over here, because indirectly it would mean that she will give a medical certificate for that period. All right. So what do you have to find in this? You need to find the maximum number of days Alice will be marked present after performing the operation at most once. All right. So you are given the power to do this at most once. Now, n is an order of 10 to the power 5, right? So that means expected time complexity is an order of n, or maybe n log n is maximum you can go. So we need to come up with a very single for loop based solution, right? If we can come up with some solution of that case. Now, if I look at the test cases per se, test cases and the problem statement is going to be pretty simple to understand that, right? If you look at, let's say, the last case, you understand that, all right, she was absent for 0, 0, then present, then 0, 0 absent again, then 1 present. Now, what she would have done is she could have selected, let's say, this segment, and she could have turned this whole segment of zeros into 1. Then she would have had attendance of 4 days, 1, 1, 1, 1. Correct? That is why the answer turns out as 4. So it's pretty simple, right? Target is to find what is the longest zero segment length that is coming in the problem, and then I think we are good to go. All right. So if I actually write out the claim in this case, claim is simply to say that, let's say, present days were actually D. These are the days that Alice, I think, right? This is Alice, or yeah, Alice. Alice is present. So let's say D was the count of days she is present. That means D is the count of one character that is coming in the string S. On top of this D, you are given the operation to do one time. And that operation is telling you that, all right, if I had some S1, S0, S1, S2, till I had some Sn, you will take up a segment of zeros and convert it to all ones. Let's say this segment of zeros you took, maximum segment out of those would have been preferred to maximize the count of present days. So maximum number of zeros, let's say they occurred, let's say maybe Z times. Then you know that D plus Z is your answer. Because D were already present, D was something Alice was already going on these D days, and this Z days, which was coming as a continuous 0, 0, 0 looking like structure, you converted everything to, let's say, 1, 1, 1 structure. So that means now you got D plus Z days of total present of Alice. All right, so now how do I find this? Very simple piece of code, right? You must have encountered this piece of code many sort of times. This is going to be a very simple counter-based algorithm. You are off with a good start. You say, all right, I am standing in the string. I am going to traverse the string from left to right. And then I'm going to say, all right, when I'm traversing the string from left to right, then I can keep maybe a counter of zeros, which I can say CZ equals to 0. And then maybe I can keep a MZ, that is maximum zeros. I find that is also 0. And then I can start counting. I begin from the left-hand side. And if I'm beginning from left-hand side, I first check, is S0 equal to 0? If yes, then I can increment CZ. And I can keep on doing this till I find a 1. As soon as I find a 1, I know I have just exhausted a segment. So I can now take this value of CZ and make MZ equals to max of MZ comma CZ. And then I can turn CZ equals to 0 again. Because now I've encountered a 1, that means I have broken out of a segment of continuous zeros. So very simple piece of thing to understand, right? Very simple piece of code, very simple piece algorithm. You run a very simple loop left to right, start checking for continuous segments, increase till you are actually finding a continuous segment of 0, and just reset the counter back to 0 with a maximum taken value out of a mean MZ answer. And then D plus MZ can be your answer. D is already the number of ones you have counted in the particular string. All right, so if you look at the piece of code now, going to be pretty simple. Took a variable for test case, took a variable for N, S, so pretty much input taking. Now I've taken a variable for count of ones, right? So this is count of ones, starts from 0. I first loop in the string, and then if anything is equal to 1 character, I increment the count. So this is actually D, the starting D value I'm talking about. Now I've taken two variables. One is 0 segment, one is max 0 segment. So 0 segment is basically CZ, which takes out a 0 segment value, and then max 0 segment is something I'm going to max out with. So both start with 0. Go in the loop. If IT is 0 character, increment 0 segment by 1. And if it is not, that means 0 segment has to be reset back to 0, and I can max out this current 0 segment length with a max 0 segment variable. And when I come out of this loop, I will have to print this line again, or actually execute this piece of line again, because I know that it can happen at the end. You were finding all zeros, then you need to maximize that also. Correct. So simple thing to understand. And then I can print max 0 segment plus count of 1. And this is going to be the answer to this problem. All right. So if we discuss the time complexity pretty simple to understand, right? You are going to have definitely a loop running over here that is running in n complexity, and then a loop running over here that is running in n complexity also. So overall time is simply O of n. Correct. And as for space, I'm not taking any extra space to any data structure space to store anything. So space is pretty much constant, right? Simple variables. So I hope the problem has now become clear. So this is end of problem 1. We can actually move on to problem 2. All right. All right. So yeah, problem 2. Problem name is binary minimal. How does it go? It tells you that Alice is given a string S of the length n. Now it is written that she can perform the following operations on string S. Operation tells her that you select an index in one-based indexing between somewhere in the S length, and you delete that character Si. Or else the second kind of operation tells you, you flip that character Si. So if it's 1, it becomes 0, or vice versa. If it's 0, it becomes 1. Now it's very clearly written that you have to find the lexicographically smallest thing. So this is condition number 1. And second condition is you are going to use at most k operations. So this is a pretty much crux of the problem. If you were not given this limit, then this problem had no sense. So you are going to do this at most k number of times. In that, you will find the lexicographically smallest string. So a very small definition of lexicographically smallest string is given over here. I think this is pretty much simple to understand. You have a string S, you have a string Y. You say that X is lower than Y if the smallest index I where X and Y differ, Xi is actually lower than Yi. All right. So this is lexicographically concept. Now you say, all right, I have a total of n, I should say size, and then k is also belonging in n size. So I can now say, let's say I'm talking about this test case. So you had 0, 0, 0, and you had one operation left with you. So they have said that you will remove any one of the 0 and you will receive a string that is 0, 0. Correct. Now, let's say the string was 1, 1, operation count was 0, so not a big problem. You get 1, 1 again. So test cases, sample test cases are pretty weak to understand, right? That means we need to actually look further, solve of our own test cases to come up with a good approach for this problem. All right, so first we'll try to generalize some ideas. You have a string S, length is n. That means the characters are S1, S2, S3, S4, S5, so on till Sn. And you are given the limit k. So now first idea, what is the first thing we need to understand? First thing we need to understand is there is a definite simple thing. If let's say this is a binary string, either it has a 0 or it has a 1. So if let's say you are trying to compare two lexicographically strings at some particular position, let's say one of the possible answer you thought was some string that looked like S1. And one of the possible answers I said was something like S2. Now, lexicographically, if you say S1 is less than S2, that means there is a 0 and there is a 1 in S2. If S1 is less than S2, there is a 0 at this place and there is a 1 in this place. Maybe everything is matching up till here, then you find a 0. So lexicographical concept is pretty much simple. Because of this concept, I get an intuition. What is this intuition? This intuition tells me that since I am not at all, since my main target is to pretty much say ones are something that should not come up in my strings. Since I am bothered about I am bothered about the ones in the looking string. So first I can actually think in this direction that if k operations that are given to me, they are sufficient. What do I mean by sufficient? Sufficient means if k is actually greater than equal to the count of ones that are coming in the string, then do you think you are good to go? Do you think you need to form any answer? Like, do you think you need to think beyond this? If let's say k, that is given the number of operations, are actually greater than the count of ones in the given string, then what can you do essentially? Let's say maybe k was given, let's say maybe k was given some value, and you said that in your string, let's say this was one, maybe this was one, then there was a random one again, maybe some random one again, so and so here. But the whole problem is k was given greater than equal to the count of ones. So you could have said that whatever string I would have created, if that string has no ones in it, then definitely that is much more optimal thing to do. Is that right? So what operation should I follow? This is the next thing to think about. What operation should I follow? I have understood that ones are something I should not go ahead with, right? Ones in my string is not going to be a good thing to look like. If I have one at this location, I would have actually preferred that there is no one over here, because from the left hand side, if this would have been a zero, that would have been a better case, definitely, because zero is lower than one. So lexicographically, it forms lower string than one. So I know one is something I don't want. Now, remember, I just stated I don't want one. Do you think you can convert 1 to 0? What operation do you actually think you can do or you should do if you find a 1? Let's say k is greater than equal to c1, as I mentioned. This is case 1. I say case 1 is k is greater than equal to c1, and then we'll talk about case 2, where obviously, naturally, by common sense, k is less than c1. So I bifurcated two cases. I say k is greater than equal to c1. Now, in this case, I am saying that you have the possibility to operate on the ones. Now, operation is of two types. One tells you that make the 1 to 0. Other tells you remove that one. Remove that one. What do you think is going to be ideally the better case? Ideally, the better case is going to be remove that one. Why? Why? Let us try to understand this. Let's say the string looked like 0, 0, 1, 0. And k was given 1 to you. You could have said, all right, let me convert this 1 to 0. So first case, you would have said, I get a string 0, 0, 0, 0. And I would have argued that don't flip this one, rather remove this one. If you remove this one, I would have gotten a string 0, 0, 0. So both of us are doing the same thing. That is, we are indirectly making the existence of one in our string no more. We are removing ones totally. But you are flipping one and I am removing one. That means my string S1 I would have formed and your string S2 you have formed, both contain 0. But S1 length is lower than S2. So this is also the next case, actually. Lexicographically, in a dictionary format per se, 0, 0, 0 would have occurred before 0, 0, 0, 0, because the length of the string is lower than the length of the above string. That means it is optimum to simply say, what should I actually do? I should remove the ones. Is this clear? I should actually go ahead with the operation and say, if I have k greater than equal to c1, that is count of ones in the string, I can remove those ones totally from the string and only take up zeros. Now, I have taken a case k greater than equal to c1. So what can happen is, after you, let's say k was greater than equal to 1, that means let's say maybe k was 7 and c1 was 3. Maybe you had 3 ones coming in the string. This is c1 and you had k operations left with you. So you would have utilized 3 operations to remove these 3 ones totally. Now the same argument follows. Everything looks like 0 in the current string. Now anything you do is simply saying flip or remove. Now you don't want to flip, right? If everything is 0, let's say in this case only, let's say after doing this, you had a string that looks like, let's say in this case, you had k equals to 2. Correct? K was 2 in this case. So you first argument says, use up k till I would have removed this one. So string I get is 0, 0, 0. Now k is left with 1. Now, do you want to flip any 0 again? No. If you flip, not going to be a good case, right? If you flip, you make a 1. That means you will somehow or the other increase your string in lexicographical manner. So you have a k1 left with you. By the same logic of receiving as lowest size of strings as possible in a dictionary format, don't you think I can remove a 1 again? Remove a 0 again and utilize this k operation and make it 0. So the argument simply becomes, if k is greater than equal to c1, you first utilize c1 times to remove all the ones, and then whatever is left, you utilize them to remove all the zeros. or indirectly saying, if k is given to you and k is greater than or equal to c1, if length of string is n, then you form a string that is having the length n minus k of all zeros. Because it will indirectly mean that you have removed k characters from the string, and now the string is all zeros at all. Is this clear? Is case 1 clear? I hope it is clear, right? So now we can actually move on to case 2. Once case 1 is sorted, I can move to case 2. What if k was less than c1? That means there were some ones in the array, but I was not at all given the option to actually remove all the ones. There would be still some ones left. Now, if you know very well that, let's say in this case, let's say I was given a string that looks like 0, 1, 1, 0, 1, 0, and k was given, let's say 2 to you, then that means you can remove, by the same logic I followed, you will remove 2 ones. You will not flip them, you will remove, because you also want to parallelly minimize the size of the string. It makes sense to minimize the size of the string because lexicographically then you might receive lower in the dictionary format. Might, not sure, but might. So that means if k is equal to 2, you wish to remove 2 ones. But which k ones do you think you should actually select? I could have argued you can go with these 2 ones, or maybe you can go with these 2 ones, or maybe you can go with these 2 ones. What do you think is going to be the optimal? Optimal is actually going to be simply by a very simple common sense logic that if I'm thinking in a direction of lexicographically manner, I want that from the left hand side, I have lowest characters as possible. By what do you mean by lowest? Smallest characters I can make. Smallest character I can go is actually 0. So do you think I should follow this operation? If I follow this operation, that is operation number 1, string that I will receive will look somewhere like, somewhat like, I would have, let's say, gone with this operation. I would have received a string that looks like 0, 1, 0, 0. If I would have gone with this operation, it looks like 0, 0, 1, 0. And I would have gone with this operation. What does this look like? It looks like 0, then you have a 1, then you have a 0 and a 0 again. So what do you think is the lowest out of these 3 strings? Definitely this string. And how did this come up? You greedily said that from this left-hand side, what should I have done? I would have removed greedily whichever one was coming first till k was getting exhausted. So I would have run a loop from left-hand side. As soon as I encountered a 1, I would have said, remove this one and decrement k by 1. Now, if k is still left, keep on going. Say, all right, one more 1 received, remove this one again. And I'm good to go, k minus minus again. And I would have break this for loop of a string wherever k turned out to be less than or equal to 0. By this, I would have greedily first reduced or removed rather all the ones from the left-hand side. And since I know I am talking about lexicographically manner, I should have preferred to remove ones from the left-hand side because that would have created more number of zeros in the left-hand side manner, thus giving me the better lexicographical string. All right, so I hope this logic has become clear. So I have bifurcated the 2 cases based on the intuition that k is given to me and k is giving me the power to remove 1 totally. So first intuition comes from the fact that as compared to 0 and 1, 1 is a good thing to remove. If that is clear in your mind, you will easily able to visualize these 2 cases. That means k greater than or equal to c1, best option available, totally take out all the ones, make them go away, and finally, whatever are left, make some zeros also go away and report a string that is of n minus k length, all zeros. And if that is not the case, then you will have some constraint, and that constraint can be solved by simply thinking in such a direction. Lexicographically, smallest string is required. Let me traverse from the left-hand side and greedily reduce whichever one I first find. All right, so I think the problem has now become clear. Now, if we look at the code part of this, all right, so this is the code, right? Taking the input for n and k, taking the input string, taking the input for test cases. Now, I'll count the number of ones in this particular string. All right, so this is, if this is 1, then I'll increment count of ones. Now, simple check, case 1. If k is greater than or equal to count of ones, I make a new length, that is n minus k. I make a string a, initially empty, run a loop from 0 to new length, and increment a by a single character 0. That is simply creating a string of all zeros of n minus k length. Now, I'll report this string. And else, if I go in the case 2 format, that means I'll be forced to check which string should actually remain now. and which string should not remain at all. So I would have said, all right, now what should I actually do? I should now actually make S of I. If S of I is equal to 1, I can make S of I equal to 0. Is that right? And I can finally print this case. All right. So I hope now the problem B has also become clear. Is there any doubt to this? No. All right. So I think we are good to go. We can move on to actually problem C. All right. So this is also an interesting problem. This is basically an observation-based problem, I should say, actually. All right. So we'll read this problem, bucket game. There are n buckets where ith bucket contains AI balls initially. And Alice and Bob decided to play a game with the following rules. Now, both player takes turns with Alice going first. And if there are no balls left, then the game ends. All right. And it is written that if it is his or her turn, then the player will remove a ball from any bucket which contains at least one ball. And now, if after the move, the bucket has become 0, that is empty, then the player gets the point. Now, if both players play optimally, find the player who will get more points. Basic stuff, you have to report, get the most number of points, and you report which is the winner. If both gain same points, you print draw. All right, so n is given to me, pretty huge, 10 power 5 order. AI is in 10 power 9 order, right? So if you actually try to simulate this process, you will not be able to do that, right? You cannot simulate this out of AI and say, all right, I'll decrease AI one by one every time. That is not going to be a good method to go about. So brute wise, if you think you can actually simulate the whole process in a very brute manner, you cannot do that because AI is pretty huge. That means you need to come up with some good observation in this case. All right, so we'll start discussion with some observations. The problem has become clear, right? The problem has become clear. This case is given to, let's say, according to this case, the answer is Alice. According to this case, the answer is Bob. We'll discuss why is this answer coming. But let us try to first observe some things. First argument is, idea one is, the array elements are from 1 to 10 to the power 9. Is that correct? Now, since they are from 1 to 10 to the power 9, you know that the array can contain some ones. So initially, I have the turn, which is equal to Alice. And let's say I have some ones in the array. Let's say some numbers are 1, maybe let's say some other numbers, something, something, then maybe one more 1, then something, something, maybe some 1. So let's say there were 3, 4 ones coming in the array. Now, every player is playing optimally. So what do you think is going to be a first idea? First idea is going to be very natural instinct, right? Since it is a player's turn and you see that there is some bucket with a value 1, then don't you think that player is going to pounce on that bucket and grab all that ones? Correct. So that means if I'm starting with Alice, I have some number of ones. That means the initial turns of the events is definitely going to look something like simply saying, let's say I have 4 ones in the array. Let's say I had 1, 1, 1, 1, 1. Then I begin with Alice. I say Alice is going to pounce on this 1 and take this bucket, increase her point by 1. So if this is Alice's point, this becomes 1. This is Bob's point. This becomes 0. Next time it is Bob's turn. Bob says, all right, this 1 is gone. I have 3 more ones. I should bounce on a bucket that is having the value 1. I will take that bucket and increment my point. Next time Alice says, let me pounce on the other bucket, increment my point by 2. Then Bob says, I'm going to pounce on this final bucket and increment my points by 2. So is this pretty simple to understand? This is pretty simple to understand, right? Basic intuition. Idea one is all the ones are there. Every player is trying to play optimally. So first idea would definitely be if there are any ones in the array, you will try to exhaust them. And on the basis of those ones, you will finally now decide whose turn is it now. In this case, let's say the number of ones were 4 or actually even. That meant if the turn started with Alice, the turn ended on Alice. Right? That means that now the turn will also start with Alice again. That is what it means. Because Alice, Bob, now the turn is again to Alice. So if there are even number of ones in the array, that means the turn is definitely Alice's again. And if there are odd number of turns, then the turn is definitely Bob's. Is this clear? That means what I can do is, yeah, correct. We'll come to that idea. And now what I can do is, we can say, I have the pointer, their pointer variables that are with me, that is points variables, sorry, with me, Alice points and Bob points. So I'll simulate this first process first in hand, start with the turn equals to Alice, if count the number of ones, if even increment whatever points should have come for Alice, whatever points should have come with Bob, and given the turn back to Alice, else given the other condition, given the turn back to Bob and incremented their points likewise. Now all the ones are exhausted from the array. Now anything in the array that is present is greater than equal to 2. So now you know AI is definitely greater than equal to 2. AI that are left in the bucket in the array is definitely greater than equal to 2. That means you might have some 2s, maybe you will have some other numbers, so on, something. So I'll take up this case. Now in this case, my claim is 2 is a big problem. Why do you think 2 is a big, why am I saying 2 is a big problem? If any bucket has a value 2, then what can happen is, let's say player that was playing is Alice. And Alice said that this 2 bucket, I am going to take 1 point from it. If Alice does this, this bucket becomes 1. And the next time there is Bob. Bob sees this one and Bob will say, all right, this is a pretty good opportunity. Let me pounce on this one and take up an extra point. So if Alice played a condition where she operated on the 2, did she actually increment her point or did she give the advantage to Bob? She gave an advantage to Bob. And because every player is playing optimally, she is not going to do that. That means if there is a 2, any player that is playing at that current turn, he or she will prefer not to go to that 2, not to operate on that 2. Is this clear? That player, if there is a 2 in the array, that player is going to defer from using that 2 as long as possible. He or she will not try to use that 2 unless it is necessary. That means idea 2 comes that if I have some 2 in the array and if I have some other numbers in the array, first the players will try to differ from reducing any value beyond 2 and first actually try to operate on the other buckets which have a value greater than 2 and bring those values down to 2. That means now if Alice is standing and Alice knows that it would not have been optimal to play 2 or this 2, she would have played this 3 and made this 3 to 2. Is that right? And next time, Bob's turn would have been there. Now, Bob would have said, I have a 2, I have a 2, I have a 2. Not optimal to play these 2. Because if I would have played these 2, Alice would have gotten a point in the next turn. Not optimal. I should go ahead with this 5. I should reduce this 5 to 4. And I'll be good to go. My turn is exhausted and Alice does not get any advantage. So this becomes 2, 2, 2, 4, 6. Now, next time Bob says again, Alice says again, Alice's turn, Alice says again, all right, 4, 6 is there. I should play with these terms, not go to 2 again. So I'll reduce this 4 to 3. Next time Bob does something with 3, so on, then 6, everything. Finally, this simulation goes on and on and on and on till you are forced to actually create, the array has been created that looks like 2, 2, 2, 2, 2. And now whichever player's turn is there, that player will be forced to operate on these 2s now because there is no other element that is greater than 2. That means the player is now forced to work on a 2 and that player is at a disadvantage. That player is at a disadvantage because now, you know, let's say Alice's turns were there. If Alice would have operated on any 2, Bob would have taken that 2's 1 and incremented his point. If Alice operated on this 2, this becomes 1. Bob would have said, let me pounce on this 1. I will take its point. Next time Alice's condition again, Alice would have said, all right, 2 again. Not a good thing to do. I am still not good to go. If I even take this 2, Bob will again pounce on this 1 and I won't get a point. Bob is going to get a point. So the person whose turns is there after the whole process is simulated to create an array that looks like all 2s is at a disadvantage. And to be very mathematically claimful, you can say that that person, the other person whose turn was not there, let's say Alice was in this case and Bob was not the person who was having the turn, Bob is going to have 5 points definitely incremented in his point count. Because Alice will play this 2, he will get a point. Plays this 2, get a point. Play this 2, get a point, and so on. So total n was 5 in this case. Let's say I took an example. So Bob would increment his value by 5 definitely. So I hope the idea has now become clear. Now, if the idea has become clear, as I mentioned in the problem start, you cannot simulate this process I showed you. In this case, I showed you by rough hand that 3 would have converted to 2, then 5 would have gone to 4, 3, so on. But you cannot do that. So what is the very simple thing to, how can you actually simulate, not go into the simulation, but actually come up with a mathematical approach? Mathematical approach will be very simple to understand. You can say that I will count the value or the sum that I would have received from the extra overhead that was there for every value converting to 2. That means if this initial array looked like 2, 2, 3, 5, 6, I would have said, I will count the overhead. Overhead means converting this value to 2 as a overhead of 0 because this is already 2. Converting this value to 2 is overhead 0. Converting this value to 3 is actually 1. Converting this value to 2 is actually, converting this value to 2 is actually a 1 overhead because you need to reduce it 1 time. 4 to 2 will take 3 operations. 6 to 2 takes 4 operations. Now you sum everything up. You will have a total of 8 operations. And now we have just seen if the number of operations are even, then whichever player was playing first is going to play finally. And if the number of operations are odd, then whichever player was playing first, opposite player now plays. So this can be simulated very easily. Has now the idea become clear? All right. So we'll move on to the code part of this. Correct? I will take the test case input. I will take the size of the n input. I'll take n input. I'll take the vector input. Now I've created simple variables in this case, right? Alice score, Bob score, count of 1, count of 2s. What will I do? I will first maintain what are the ones in my particular array. I will increment wherever it is equal to 1. And next time I'll say, I am going to increment in the sum, what is the number of it minus, what is the overhead that was there, that is it minus 2. All right. And then I'm going to say, I'm also maintaining a variable that is called count of 2s. So pretty simple to understand, right? I'm simply taking variables in this case. Now I start off with a turn string. This is Alice, right? Just for you to understand. I first say, is count of 1 equal greater than 0? If it is, that means there are some ones existing in the array. If there are some ones existing in the array, what should I do? I should now check, is it odd or is it even? If count of ones are odd, that means Alice's score gets incremented by count of 1 plus 1 by 2, that is seal of count by 2. Bob's score incremented gets only by count of 1 by 2. And because this is an odd turn, you would now make the turn to Bob. Started from Alice, now Bob's turn is going to come. And if this is even, that means you will go in the else part and you will say, Alice score only turned by 2, Bob score incremented by 2, and turn comes back again to Alice. Is this clear? This small bit manipulation check is also clear, I think. Count of 1 and 1 should be clear. This is a very small check to actually check very quickly, is your number an odd or even nature or not? Because this actually checks the last bit of the number in a binary format. And you know very well that if the last bit is turned on, it is an odd. If the last bit is not turned on, that's the least significant bit is not turned on, it's an even. So a very small check over here for bit manipulation. Now, up till here, I have exhausted this initial simulation of taking the ones greedily, pouncing on the ones greedily. Now I begin with the other piece of code. Now, first I check, is sum odd? If sum is odd, that means turn will be Bob's. If turn is Alice, turn is going to be Bob's. And if sum is not odd, that means turn is going to remain same. So if this if condition is not fulfilled, that means whatever turn was up till here, that turn remains constant. And if sum is actually odd, then I need to swap turns. So I will swap this turn. If turn is Alice, I'll make it Bob. If turn is Bob, I will make it Alice. So this is to simply say, now by this operation, I would have found it out that at the end of this exhaustion of this sum variable, I would have found that is, let's say 8 were the exhaustion I would have done to create an array that looks like all 2. Whose turn was there? Which player was actually at a disadvantage? I need to find that. So that is why I have done this small operation over here. Now I have a very simple thing. If turn is Alice, who is at a disadvantage? If turn has now become Alice's, that means Alice is at a disadvantage. That means Bob's score is going to increment by whatever are the count of 2s in the array now. And if that is not the case, Alice's score get incremented. Clear? Now, very simple if check. If Alice score greater, print Alice, less, print Bob, equal, print drop. All right. So if you now discuss the time complexity of this piece of code, right? This is going to be pretty simple. I am running a loop n over here, correct? And I'm using very simple variables also. So not a big deal. So I can say that time complexity is simply order of n. And what about space? I'm using a vector to store the input. If I take that into consideration, I will have O(n) complexity. Else I can say everything is constant. So I'll take up a constant time complexity. Space complexity. All right, so good to go. I think we can proceed to the rating of the problem. I think this is going to be Codeforce's B problem for, or rather actually, I can actually take this as, yeah, this would be good to go. B problem, I think should be good to go. Somewhere around, I think 1400 problem should be a good range for this. 14 to 1500, right? All right. So ideas was a pretty important part of this, right? First, my intuition actually began from one only. This is why I should try to simulate the whole process to you. Begin with ones, then actually try to observe which number was actually not beneficial for you, which is the number in these game sums. Also actually there's an advice per se, because ideas actually start up from actually observing which number are you at a disadvantage with, which number, after which number do you think the person is not going to have any control over his points. This is the idea that mostly revolves while you solve game problems in Alice and Bob case, specifically a problem like this, where you are trying to reduce something. This is why the intuition is looking like this. All right, so we can actually move on to the fourth problem, right? This is going to be a pretty interesting problem. Now, is grab one is suboptimal? I'm sorry, I did not understand this. Is grab one is suboptimal meaning? I think the idea you have understood is clear, right? I hope you have understood the idea. We can actually begin with the fourth problem, right? For the discussion. Yeah, cool. All right. So this is a pretty interesting problem, right? And this is like this problem per se. There is a very simple piece of code in this, piece of observation actually in this to understand. But the problem with this is piece of problem is actually, I think many of you guys must have encountered a greedy solution out of this problem, because this problem was having around 400 to 500 summations. But the argument is that greedy solution is definitely wrong. All right. So the actual idea behind this problem is pretty interesting and pretty straightforward and with a well-given proof. The greedy solution you must have found out on XYZ platforms must be wrong and is definitely wrong, right? I can actually show you up a case for show you a test case also for that greedy solution if you want, if you can comment in the chat. But if that's not good to go, I can actually begin with the optimal and the exact proof of this solution. All right. So any greedy solution you must have found out on the net during this problem contest going is not definitely right. The actual solution to this problem is pretty different. All right. So what we can do is, all right, you don't know the greedy approach as well. So that's good to go, right? Greedy approach is not correct. What I'm not trying to open up anything about the contest per se, but I was just trying to give you a very brief that this problem was getting submitted by a lot of people and the solution they were submitting is not wrong because of the weak test cases. So it's a pretty good problem, but it got ruined due to pretty weak test cases. That is my take on the problem. But ignoring all that fact, just looking at this as a problem sake, we'll try to understand the problem and come up with a solution. So it's a pretty neat problem, pretty neat solution. All right. Let us go ahead with the exact solution to this. You don't need to worry about the wrong. Alice is given two arrays, A and B. Each is consisting of n integers. Note that both arrays are one-based indexing, right? So they have done a one-based indexing, not a big deal. You can go ahead with zero-based. Now you say she can perform the following operation in the array any number of times. Now this operation is very, very, very crucial to understand, right? This seems a very simple operation, and you might understand that there's no pattern behind this operation, but we'll try to come up with the pattern. All right. So AI is given as a sum. Let's say you select an I. That will force you to make AI minus 1 equal to the sum of its three terms, that is AI minus 1, AI, and A plus 1. AI becomes negative of its next term, AI plus 1 negative of its previous term, and AI plus 2 becomes the sum of AI plus 2, AI plus 1, and AI. Now, this is done simultaneously. All this simulation is done simultaneously, right? AI minus 1, AI plus 1, AI plus 2 are updated simultaneously using the old values. All right. So you don't have to, don't think in this way that AI minus 1 got updated first, and then you will use this AI minus 1 value later on. You are doing this on the previous old values, and then you're doing continuously all these four operations together, and then you proceed. Definitely the array changes, and then you try to come up with that approach. Now the question asks you, can you convert this array to a new looking array B? B array is also given to you in any number of operations. All right, in any number of operations. There's no constraint on operations. So you can use unlimited number of operations. Just tell me a yes or no answer. All right. So this is a good thing to actually think. You are not constrained on the operations. So if you try to think about simulating the process, there's no need. This problem indirectly points you in the direction that I'm not asking you the number of operations. I'm just asking you, can you do it? So problems like this should give you an intuition. I should not step into actually simulating the process. I should actually try to first come up with a solution. I should actually think in such a way where I can answer this problem in a yes or no format or no. So there's a proofing behind the problem. Now they have given a very weak test cases in the sample also. So there is no idea that is going to pop in your head directly for this. They were talking about the third case, 0, -3, 4, 0. You take up 1, -4, 3, and 1. Now they have said that, all right, take it this I equals to 1 in this case, or I equals to 2 for the 1 based indexing. And you switch up everything according to their 4 operations, and answer pops out as yes, because let's say this becomes actually -3 goes this side, this becomes 3, 4 comes negative this side, -4. This becomes a sum. So this is 0 plus -3 plus 4, this is 1. And this also becomes a sum. This is 1. So array looks now 1, -4, 3, and 1, which is good to go. So they have printed yes. All right. So not going to give you a very good intuition per se for the sample cases. All right. So now what am I going to do? I'm going to show you a generalized case for this. And I'm going to make up an idea that is going to be very crucial to the problem. All right. So I'm going to take a general case. Let's say n was given 6. I will talk everything about in variables. I'm not going to confuse in any literal values so that anything doesn't look like a simple, I should say, pattern. It is going to be a very crucial observation. You say, all right, I have n equals to 6, example, and n is given greater than or equal to 4, right, in the problem. So you're not going below 4. So n is given 6 to you. And you say, I have a number A, B, C, D, E, and F. All right. Now, just say, for a sake moment, I say, do this operation on these first 4 elements. Do this operation on this first 4 elements. What do you think is going to be the answer? If you do this operation on the first 4 elements, what do you think actually pops up? You simply say, what pops up? This goes this side, this goes this side with a negative value. This becomes -C, -B. I have a plus B plus C, and I have a B plus C plus D over here. Is that right? Now, if you look up this operation directly, if you start simulating this process directly, I have also done this. If this makes no sense, I have also done this. I have also made up so many observations you can see in the green pen to actually come up with the observation so as to see what pattern can I follow. The claim over here is you can actually make a lot of general variable additions in this case. Maybe A can become some other values also. You can now begin with saying, I could have done the operation on B, C, D, E, then maybe C, D, E, F, then maybe again on B, C, D, E, that could have operated something more, then so on, so on, so on. Not going to give you any pattern per se, right? The claim is, I have done this. I think you must have also done this on pen and paper. You will not see a very direct observation by simply doing this operation so and so again, just to see. First intuition might have been in your head that maybe there was some constraint on every problem, constraint on every value, but that is not the case. Constraint on the problem, constraint on the value comes up from this idea that I'm going to write this in green pen. All right. So you try to understand this. I am going to create a prefix array of this array just for a comparison purpose. All right. Sum is constant. That is definite. Sum is constant. I'm going to come to that fact. Sum is definitely constant. Sum is constant. Why? Because if you want a proof of sum is constant, you easily can see, let's say these 4 numbers were only given to you. Now, if you sum up these 4 values, initial 4 values were AY plus 1, AI, A plus 1, A plus 2. Now these 4 values look like these. If you sum up them, if you sum this, plus this, plus this, plus this, you will again receive back the sum. So sum is constant, right? But even numbers can never be odd. No, that is not the case. Observe this. I will create a prefix array out of this. All right, so I'll mark this in blue pen. You understand a prefix sum array? Prefix sum array means from the left-hand side, I'll say A. Now I have A plus B. I have A plus B plus C. I have A plus B plus C plus D. I have A plus B plus C plus D plus E. And then I have A plus B plus C plus so on till F. I have created a prefix sum. Why am I doing this? Understand this. Now, initially, your prefix sum looked like this. Correct? Initially, your prefix sum of the original array looked like this. After you did this operation, find the prefix sum again. The numbers were now E and F. My claim is find this prefix sum again. I will mark this with blue again. So this is before operation, BO. Before operation, your array looked like, prefix sum array would have looked like A plus B plus C, so on. Is this clear? Now, after doing this operation, this is the new array. The new array's prefix sum, if I find that, what is it going to be? This is going to be A plus B plus C. This is going to be A plus B. This is going to be A. And this is going to be A plus B plus C plus, this is going to be A plus B plus C plus D. Can you see a very simple observation over here? Yes, correct. Just value swap. Exactly. That means other prefix sum is definitely same. This is definitely A plus B plus C plus E. This is A plus B plus C plus E plus F. But what did you observe over here? Two values got swapped. A plus B prefix remained same. A plus D plus C plus A plus B plus C plus D remained same. But what changed? Change was over here. This A shifted this side, this A shifted this side. Or rather, actually, above is actually the new operation. This A prefix came over here and this A plus B plus prefix came over here. Is that right? When did this happen? When you took an I equals to 1. I'm doing a zero-based indexing, so you took I equals to 1. Now the claim is, can you picture this clearly that if you would have taken an I equals to 3 now, let's say you took an I equals to 3, the new elements that look like are now like this. These are the new elements in the new array. Now, if you have taken I equals to 3, that means you will be operating on these elements. By the same proof, don't you think now when I would have done this, the prefix sum of the elements kept in, let's say this was the new prefix sum, this was new prefix sum. Then if over here there was A and over here there was whatever prefix sum was there, that was A plus B plus D plus E plus A plus B plus D plus C plus D plus E. Don't you think these two will get swapped again if you have done in this operation for I equals to 3 by the same logic? Yes. So the observation is actually to understand that in the prefix array, prefix sum array of, correct, exactly, in the prefix sum array of the array A, if you take up all the odd positions and you take up all the even positions, so you take up all the odd positions in the prefix sum array, take up all the odd positions in the prefix sum array, then you take up all the even indices positions in that same prefix sum array. You find these numbers, let's say these numbers were looking like this, you find these numbers, let's say these numbers were looking like this. Now, if you do the same thing for the array B, if the array B that is given to you, which you are trying to as a target form, you find the prefix sum on that, you find the odd indices prefix sum values, you store that, you find the even indices prefix sum values, and you also store that. Now, do you think if these two prefix sum arrays you just found out are not equal, that is the odd prefixed sum values out of the prefix sum array of A is not equal to the prefix summed odd values of B, or for even same case, then don't you think answer is no? Yes, the answer is no. And if the answer is yes, then that means these array are definitely same, or the values in the prefix sum of odd and even for A are same, equal to the odd and even indices for the prefix sum array you created out of B. So the array is the idea now become clear. This is a very good problem to understand, right? And due to weak test cases, my claim was that this problem got a bit butchered, but this problem is actually very good. All right, so I think the problem idea has now become clear. Now, there is going to be a very small corner case in this also. That corner case I'm going to mention in the code part itself, right? Above this, you can also imagine one thing same, that the last prefix sum, that is A plus B plus D plus E plus F. Do you think that last prefix sum is going to get changed? No. That means indirectly that is simply saying sum is constant. So that means the condition which you must mention, the condition you just mentioned, I think, yeah, you just mentioned the condition, that is the corner case in this. So above the fact that these prefix arrays should match, there is another case, there is an added case on top of that these sums should also be constant. So I'll be checking both conditions simultaneously. All right, so I can make a prefix sum of A, then take out all the odd indices values and maybe store that in a prefix sum odd. Then I can store that some other values in prefix sum even. This is going to be for A, this is going to be for A. Now I'm going to do the same for B. I'm going to check their equality. If they are equal and the net sum of array A and array B are equal, then I'm good to go. I can print yes, because I have mathematically proved that the sorting is only happening between odd indices and the prefix sum is prefix sum are good to go. And if any condition fulfills, any condition does not fulfill, I will go ahead with the no. All right, so I hope the problem has now become clear. The idea has now become clear. This was the crucial observation in the code. Now we can actually look at in the code part. All right, so you can actually find this code also in the editorial solution, right? I have taken up right and right from there also. So there is no confusion per se. All right. All right. So you have cases, right? This is actually going to be T. You can take this as T. Then what I've done is, since test cases are inputted, right? Then I'll take a variable N. Then I'll take a vectors. One, I'll call this as, I can call this as P1. This is the A vector and this is the P2 vector, that is the B vector. And then I'll create a prefix 1 odd, prefix 1 even, P1 odd, P1 even, P2 odd, P2 even. Then I will input the P1 array. While inputting, I'll be simultaneously creating the prefix sum. And if index is odd, I push back the value of P1 of I in P1 0, else I push back that in P1 of E. And I do this same thing for the B array also, right? So simply saying, creating this PSO odd, PSO even for A, creating this PSO odd, PSO even for B. Naming can be anything. Now I sort them. I sort this, I sort this, I sort this, I sort this. I do 4 sorts. Now, when I sort this out, I will check a very simple condition. Are these two arrays same? That is, odd values of prefix of A equal to odd values of prefix of B. Is it equal to? And is even same? Likewise, and is the prefix, final prefix that is at the back value of the P1 array equal to the prefix of the back value of the P2 array? That means, is the net sum of A equal to the net sum of B? If all these 3 conditions fulfill simultaneously, a yes is printed, else a no is printed. All right, so I hope you have well understood the problem. All right, so I think you can see it is going to well pass on the cases also, and this is going to work on the platform too. All right, so this brings us to the end. I think we can actually quickly discuss its time complexity, right? Not going to be a big deal to discuss the time complexity per se. You can say I'm creating prefix arrays. This is N, and then I'm sorting. So average case is N log N, right? If N is the size, I'm doing N log N solutions. So time complexity is N log N, right? Where N is actually N by 2, you can say, because I'm halving the indexes, but overall space time is N log N order. And space is definitely N, because I'm using N-sized arrays to actually store up this information. So I can say N is a data structure array I'm using extra. Well, it's a space and time are now pretty much clear. All right, so this brings to the end of the solution discussions, post-contest discussion for this starters division 2. I hope you like this. This is where we can stop. All right.